Let's see how we can express time and space complexity. In the earlier lecture, we have discussed what is time complexity and what is space complexity. We also saw that they can be expressed as a function of n. And what is n? N is the input size for a given instance of problem. So suppose, for example, we are computing the Fibonacci series. So whether we have to compute the first 10 terms or whether we have to compute first 100 terms of the series, so that input, what is the input for that particular instance of the problem, that is the input size. And the time is also a function of the input size, and the space complexity is also a function of the input size. So why do we think that this complexity is required? First of all is we should know that what is going to be the rate of growth of the complexity of the algorithm if the input size of the problem increases. And based on that, we will be able to find out which algorithm is more efficient. So any algorithm which is taking less time and less space is the one that is preferred. So how do we compute how much time the algorithm will take? So we know that a machine which is executing more instructions per second is going to take less time, right? So how can we estimate the running time of the algorithm? If we know the number of operations of an algorithm, and if we know the time that is taken to compute one elementary operation, if we multiply that, that will give us the running time of the algorithm. So the way of doing it is to run it on a machine and then check the time that is required to run that particular algorithm. So here if you see, this is a way of doing this. If we have a program, some function for which we have to compute the time that will be required to execute, we use a library function which is called clock. This function returns the clock ticks that elapse when a particular function is being run or when it is being called. So here we have declared two variables of this clock t type. This is a library that can be used, time.h, and we define two variables, start time, end time, and the total time that has elapsed. So at this particular instance, we note the clock time, and that is the start time. Then the function is called and it is run, and just after the function is returning, we note the time again into a variable which is called the end time. So what is the total time that elapsed for execution of that function? End time minus start time. And this is only the clock ticks that have happened. That means the clock pulses. So now to convert that into seconds, we will divide it by the frequency, which is clocks per second, and print the time that is taken. That means that if we want to compare two algorithms A and B, we should first program or write a program for algorithm A, write a program for algorithm B, and run both the algorithms on the same machine and then check the execution time. That is one way of doing it, but that would involve the programming of the algorithms. Also, the execution time will depend upon the microarchitecture of the machine on which it is running. So we have to run both the programs on the same machine to compare their execution time. So rather than writing a program and then comparing their execution time, is there any other way where we can do so and compare two algorithms without checking the actual execution or runtime on a particular machine? So let's look at that. Here you have a graph where you see on the x-axis you have the x variable and on the y-axis we have the y variable. And there is a straight line over here, and how can we define the relationship between y and x, it is a linear relationship, and we can say y is equal to 0.75x plus 1.2. So we say y is a function of f. We have seen that the space and the time complexity are a function of the input size of that particular problem. So that means we can write this as t is a function of n. And in this course, since we are doing only the time complexity, we are not focusing on the space complexity. So we will just talk about the time complexity part. So here time is the time of execution and n is the input size of the size of the input for that particular algorithm. So if we have a relationship like this, then n will be on the x-axis, this will be the input size, and t, which is the time taken for that particular input size, time taken for the algorithm to run for that particular input size, that we can plot on the y-axis. So as I said, the example of Fibonacci series, there are two ways of solving this problem and computing the terms of the series. One way is we go iterative. So this is the algorithm, which is in an iterative manner. You have a for loop, and based on the values of the variable I, this loop will be executed and the terms will be computed. Another way of solving it is using algorithm B, and this algorithm B is using the recursive method. So here you can see it is using the recursion type. So how can we say which algorithm is better? Is A better than B or is B better than A? So suppose if we have to plot T versus N now, and we say that if the input size, this is the input size n, that means how many terms of the series have to be computed. Suppose n is 10, then what is the time taken? Suppose the time taken is t1. What if n is 20? What will be the time taken? Suppose the time taken is t2. What if n is 50? What will be the time taken? What if the value of n is 100? What will be the time taken? If we can plot this graph for both the algorithms, we will be able to find the comparison and we will be able to say which algorithm is better when the input size increases. This, suppose if it is a linear line, here it is not coming. So suppose these were the values, and if it is a linear line, we say that the time complexity is the order of n, because t is now a function of n. So we say that this is a linear relationship, so the time complexity is of the order n. There is a possibility that the relationship between t and n would be quadratic in nature. So here instead of n, this could be quadratic in nature. Then we would say it is of the order n square, or the relationship between t and n could be logarithmic in nature. So then we say it is of the order log n. So depending upon the algorithm, how it is behaving, or what is the growth rate of the algorithm. By growth rate we mean what is the time being taken by the algorithm if the input size is increasing. That is called the growth rate. So if n increases, how is the time taken by the algorithm increasing? So based on the growth rate, we can say that this particular algorithm is better than the other one. So obviously you can see as the growth rate increases, as n is increasing, log n would be the best bet, because here though n is increasing, the time taken is not increasing now. So we can say an algorithm with a growth rate of log n is better than an algorithm with a growth rate of n, and an algorithm with a growth rate of n is better than an algorithm with a growth rate of n square. So this is how we can compare two algorithms. So if we have the growth rate of two algorithms as a function of n, so here you can see this is n and here is the time. So suppose there are two algorithms A and B. So if this is algorithm A, which is requiring time Ta, and the growth rate is n square by 5, and there is another algorithm TB whose growth rate is 5n, which algorithm is better? So depending upon the size of the input, which is n, we can see. Suppose if n is 1, then Ta is going to be 1 upon 5 and Tb is going to be 5. We can see that Tb is more than Ta. If the value of n is 10, then Ta is going to be n square 100 by 5, which is 20, and Tb is going to be 5 into 10, which is 50. Again we can see Tb is greater than Ta. What if the size of n becomes 100? Now this is going to be 100 into 100 by 5, and this is just going to be 500. Now we can start seeing that Ta is more than Tb. So as n is increasing with higher values of n, this is how algorithm A is behaving. It is requiring more time. So initially when n was less, TB was requiring more time, but we see that as n grows, algorithm A requires much more time compared to algorithm B. In fact, after n has reached 25, this is the point where both the algorithms are requiring similar time, but after that the growth rate of algorithm is much higher as compared to algorithm B. So we say that algorithm A is not very much efficient, and we can say that we will prefer algorithm B over algorithm A. So this is how growth rate helps us to identify which algorithm we can, or which algorithm will work better.